Rational functions graphing. Hopefully you remember some of this from last year with the end behavior and the vertical asymptotes and the horizontal asymptotes, etc. I'm going to push pause, take a minute to write this down. The biggest problem I always see is the horizontal asymptote / end behavior. So we're going to take a quick review look at that. I think everything else you probably have a good handle on. And then what happens on each side of the vertical asymptotes? Is it the same direction, opposite direction, et cetera, et cetera. So let's just practice the horizontal / oblique / end behavior. If you have some function, and I'm just going to look at the leads, you have something like x to the 4th plus blah, 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 over x to the 6th plus blah, 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 blah. Always look at the lead terms and ask yourself, does x to the 6th go into x to the 4th? And the answer is no. X to the 6th goes into x to the 4th 0 times. If you were to long divide this, which of course we're not, but the first step of long division, you would say x to the 6th goes into x to the 4th 0 times. Therefore, this would be a horizontal asymptote at y equals 0. Let's say it was something like the f of x equals x to the 6th, blah, 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 over x to the 4th, blah, 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 blah. And you were to do the same process. If you were to long divide, and you would say x to the 4th goes into x to the 6th. Well, it goes in x squared times. So this models, instead of y equals 0, it models y equals x squared end behavior. So this we would say would be up, up. Okay, what if you have the same degree? So let's say you have f of x equals 10x to the 4th, blah, blah, blah. I like blah, blah, blah. Great math terms. Over 7x to the 4th, blah, blah, blah. The degrees are the same. So if you were to long divide, and some of you are good at memorizing, and that's great. I'm not a super huge fan of that. This process works for every single rational function. How many times does 7x to the 4th go into 10x to the 4th? And the answer to that is 10/7 times. Lead coefficient. No, you don't have to show any of these steps. I'm just trying to break it down for you. Okay. So I'm going to do, actually I can fit it in here. I'm going to give you a complex problem, and we're not going to graph it. We're just going to look at the asymptotes, etc. So let's say you have something like the f of x equals, I'm just doing little bits and pieces before we do one whole problem mixed together. And you have x plus 3 quantity squared times 2x plus 5 cubed. And then in the denominator, you have something like x minus 1 times x plus 4 squared. X-intercepts come from the numerator. This is going to have an x-intercept at -3, 0. The degree is 2. 2 is even. The graph is going to bounce. So that whole bouncing crossing applies to rational functions as well. This is going to be -5/2, 0. The degree is 3. That's odd. The graph is going to cross. That same philosophy applies to asymptotes. Here, VA, vertical asymptote, you're going to have a vertical asymptote at 1. Well, it's odd. Multiplicity is 1, which is odd. So this means that the graph is going to go opposite directions on each side of the asymptote. I would just say opposite direction, not directions. And here, x equals -4. The multiplicity is 2. So the equivalent of bouncing, even is bouncing. The equivalent of bouncing is same direction. And that's going to help you a lot when you're trying to put your graph together. So let's do 2 problems. We're going to look at an oblique and yeah. Okay. Trying to get a better color here. So let's start with the f of x equals x squared plus x minus 30 over x plus 6. Okay, so we're going to analyze the graph. All right, so analyze the graph. Basically, find all the asymptotes, find all the intercepts, determine your bouncing and crossing, and then draw a nice graph. All right, I'm going to factor first. I'm going to factor first. So the numerator factors, I believe, as x plus 6 times x minus 5 all over x plus 6. And this brings us to removable discontinuities. X plus 6 over x plus 6 is removed. Before you even factor this, if you look here, you think, okay, there's a vertical asymptote at -6. That's a problem. It's a discontinuity. But then you factor it and it reduces out, you have removed the problem. The issue is no longer x equals 6. So as soon as you are able to factor and reduce, you get a removable discontinuity, which is also known as a hole. Removable discontinuity is known as a hole. So you are now left with the f of x equals x minus 5. Well, that's a line, but this is not what you were given. This is not what you were given. If you type in y equals, in your calculator, y equals x minus 5, it's going to be a line. And if you plug in the x squared plus x minus 30 over x plus 6, it's also going to look like a line. Your calculator is not going to show you the whole itself, but it will show up in the table. So great, it's a line. The y-intercept is 0, -5. It has a slope of 1. But the coordinates of the hole are the f of -6. -6 would cause 0 in the denominator, so I'm finding the f of -6, which is -6 minus 5, which is -11. You know, you're going to ask me, where do I plug it in? Do I plug in -6 to the original equation? Or to the reduced? You can't plug it into the original. If you plug it into the original, you're going to get 0 in the denominator and in the numerator. No can do. Let's just sketch our line here with a hole at -6, -11. I'm going to change my increments because I don't want to go all the way down to -11. I'm going to go by 2s. Okay, this, yeah, no. 2, 4, 6, 8. Good enough. All you have to do is put one increment on there that tells the reader. Put a 2 and whatever, that's it. So we have a hole at -6, -11. 2, 4, 6, 2, 4, 6, 8, 10. hope that's right. Y-intercept is 0, -5, 2, 4, 5. Oh no! This is supposed to be a whole. But I'm not using erasable pen or a pencil. You should be using. You should be erasing. That's not fantastic. The x-intercept is also 0, 5, 2, 4, 5. Use the straight edge. That is not the prettiest of graphs, but I'm not going to lie. I'm not going to start my video over so I can draw a prettier graph. I think you'll forgive me. Okay. So that's a removable discontinuity. You factor, 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 factor. You should always factor first, reduce, move on. All right, so let's look at another one that's got some asymptotes and some other things going on. You probably still have PTSD from that partner trio quiz from Algebra 2 Honors with the one problem and the graph was insanity. 8x squared plus 26x plus 15 over 2x squared minus x minus 15. First thing you should do is factor, so I'm going to pause here and you factor it. So this factors as you should have gotten 4x plus 3 times the quantity 2x plus 5. So we have 2 x-intercepts over 2x plus 5 x minus 3. And I am hopeful that I factored this correctly because I'm by myself. 8x squared, 20, 26, 15, 2x squared, 8. It's right. Okay. Right away, it's a whole. You reduced, right away you have a whole. What bad value of x did you take out? What discontinuity? You took out -5/2. And I'll go back and plug that in a minute. Okay, x-intercept, there's 1, and the x-intercept comes from the numerator. Value of x makes 4x plus 3, 0. That would be -3/4. Yeah, -3/4. Y-intercept, make x 0. Either from the reduced equation or the original equation, doesn't matter, you get -1. We have a vertical asymptote at x equals 3. Value of x makes this 0, +3. So we've got x-intercepts, y-intercept, vertical asymptote. Ooh, this is a horizontal asymptote. The degrees match. Guess what? The degrees were both 2. They match. When you reduce, the degrees are now both 1. They still match. 8x squared over 2x squared, 4. Or the reduced equation, 4x over 1x, 4. Doesn't matter where you try to evaluate the information. The only one that matters is when you try to find the whole. So the whole is going to be at, you know what, let me rewrite it here off to the side. 4x plus 3 over x minus 3. And so my whole is going to be at 4 times -2.5 plus 3 divided by -2.5 minus 3. Math frac. 14/11. I hope that's right. -2.5 times 8 plus 3. Okay, so let's put it all together. The nice thing is there's only one vertical asymptote, so we don't have to worry about all these different sections of the graph. All right. 0, -1, -3/4, 0. X equals 3, 1, 2, 3. For your homework, make sure all graphs go on graph paper. There's never an exception to that all year. Y equals 4, 1, 2, 3, 4. My whole is at -5/2, 14/11. Let's see, 1, 2, 14/11 is like here somewhere, and I actually made it a whole this time. Okay, it is probably obvious to you that, well, generally when you have a rational function, it's got branches and they're opposite of each other, so to speak, and opposing quadrants. But here's a way you can check. First of all, we can plug in a point. So, which I don't like doing, but let's just see how it works. So if the vertical asymptote is at x equals 3, if we plug in 4, you get 19, which is way up here somewhere. Okay, so if you plug in 4, you get 19. So yes, the other branch does lie in this area up here. The other way you know that, though, is because the vertical asymptote, x equals 3, that's an odd degree. The degree is 1. That's odd. And that means that we're going to go in opposite directions. Opposite direction. Opposite direction. Why do I keep wanting to put an S there? So if you look, there's my asymptote. From the left, we are approaching -infinity. We're going down. The graph is approaching -infinity, which means on the other side, it has to be approaching +infinity. If the left side is going down, the right side must be going up. And that's good enough for me. You don't have to plot a bunch of points. I just care that you have it in the right quadrant. Okay, after this video, I will do one that's more complex for those of you that want to hang around and see.